They rust, they grow, they decay. But underneath all of that, there's kind of this hidden language, right? A set of rules that dictates how all this stuff transforms. So in the next few minutes, we're going to decode that language together. All right, so let's jump right in with a question. Think about a rusting nail, and then think about melting ice. They're both changes, right? But one is super easy to reverse. You just pop the water back in the freezer. The other one, well, good luck trying to unrust that nail. And that difference right there is the absolute key to understanding what a chemical reaction really is. Okay, so first things first, we're going to talk about the world of change and how you can spot a real chemical reaction when you see one.
So on one side, you've got a physical change. Think about water freezing into ice. It looks different, sure, but it's still just H2O. The molecules themselves haven't changed at all. But then on the other side, you've got a chemical change. That iron in the nail reacts with oxygen in the air, and boom, you get a totally new substance, iron oxide. You know it as rust. And that's the whole point. It's something new, and you can't just easily go back.
And that process, the one that makes a totally new substance, that's what we call a chemical reaction. It's basically the engine driving every single chemical change you see. And honestly, this idea is the foundation for everything else we're going to talk about.
Now, chemists have a way to describe all this, but they don't write out long, boring paragraphs. Nope, they use a kind of secret language, a special shorthand. So let's learn how to read and write in chemistry's secret language.
Okay, so at its core, every single reaction follows this super simple structure. Think of it like a recipe. On the left, you've got your ingredients. We call those the reactants. And then, after the arrow, you've got the final dish you cooked up. We call that the products. That little arrow in the middle, it just means turns into or yields.
And this whole thing, this symbolic recipe, is what we call a chemical equation. It's the shorthand of chemistry. I mean, why write out carbon and oxygen react to form carbon dioxide when you can just write C plus O2 yields CO2? It's way cleaner, it's universal, and it tells you exactly what's going on.
But hold on, it's not just about listing the ingredients and the final product. There is one golden rule in all of chemistry. The one rule you absolutely, positively cannot break. And that rule is all about keeping things balanced. So you might be wondering, okay, what's the big deal? Why does it have to be perfectly balanced? I mean, why does it matter if we have the exact same number of atoms on both sides of that arrow? What would even happen if we didn't? Well, the answer is one of the most important rules in the entire universe. It's called the law of conservation of mass. And all it really says is this: you can't create stuff out of nothing. And you can't make stuff just disappear. Whatever you put into the reaction, you have to get out of it. Every single atom has to be accounted for from start to finish. So let's look at our recipe for rust again, but this time the unbalanced version. The numbers are just totally wrong. You can see in the table, we start with one iron atom on the left, and then, poof, we magically have 3 on the right. And we start with 1 oxygen atom, but end up with 4. Where did they come from? This recipe is literally breaking the laws of physics. So how do we fix this illegal recipe? Well, we use a pretty simple approach called the hit and trial method. It sounds fancy, but it just means you go through and add numbers in front of the molecules. We call them coefficients, until everything on the left side matches everything on the right side. It's actually kind of fun, like a little logic puzzle. And there we go. Take a look at the balanced recipe now. Once we put in the right coefficients, we have 3 iron atoms on both sides, 8 hydrogens on both sides, and 4 oxygens on both sides. See? Everything matches. It's perfectly balanced. The law of the universe is satisfied, and now our chemical story actually makes sense. All right, so now that we know the language and the main rule, the grammar, if you will, let's check out some of the most common types of reactions you'll see out there. Think of this as a quick tour of the major reaction families. First up, we have the combination reaction. This one is super simple. It's the getting together reaction. You take 2 or more things, they combine, and you end up with one single, more complex product. A plus B makes AB. Simple as that. Next, we have the exact opposite, which is called a decomposition reaction. You can probably guess what this is. It's the breakup reaction. You start with one complex compound, and it breaks down into 2 or more simpler pieces. AB becomes A plus B. This kind of breakup usually needs a little push, like some energy from heat or electricity to get it going. Then things get a little more dramatic with the displacement reaction. I like to call this the cutting-in reaction. This is where a more reactive element comes along and literally kicks a less reactive element out of its spot in a compound. It's a total chemical power play. And hey, if one element can cut in, why not have a full-on partner swap? That's what a double displacement reaction is. You have two compounds that meet, and they just switch partners. The positive part of one hooks up with the negative part of the other, and vice versa. And just like that, you've got two brand new couples. I mean, compounds. Okay, now if we dig just a little deeper, a lot of these reactions are all about swapping tiny little particles called electrons. So when a substance loses electrons, we call that oxidation. And when a substance gains electrons, that's called reduction. The trick is you can't have one without the other. They're two sides of the same coin, and they always happen together in something we call a redox reaction. And finally, let's talk about heat. Reactions can either give off heat or soak it up. If a reaction releases heat and feels warm to the touch, think of a campfire, it's called exothermic, exo for exit. But if it absorbs heat from its surroundings and actually feels cold, it's endothermic, endo for into. A perfect example of an endothermic reaction is photosynthesis. Plants literally have to absorb energy from the sun to make it work. Okay, I know this might all sound a bit like a textbook, but the amazing thing is, these reactions are happening all around you all the time. So let's bring it all home and talk about the chemistry right in your own kitchen. So, have you ever wondered why chip bags are always like half full of air? It's kind of annoying, right? Well, there's a really smart chemical reason for it, and it's all about stopping a specific chemical reaction from ever happening. So here's the secret. That isn't air in the bag. Not at all. It's actually pure nitrogen gas. And here's why. The fats and oils in those delicious chips can react with the oxygen in normal air. And that reaction, yep, it's an oxidation reaction, just like we talked about, is what makes them go stale and taste awful. That process is called rancidity. So, to stop it, the chip makers flush all the oxygen out and fill the bag with nitrogen, which doesn't react. And just like that, your chips stay crispy. You see, from the fizz in your soda to an apple turning brown on the counter, chemical reactions are writing these little stories all around us all the time. So now that you know the basics of their secret language, the world might start to look just a little bit different. My question for you is, what other chemical stories can you see unfolding around you?